Log on, tune in, find out. Another good idea from Cambridge.
It's my pleasure to introduce Professor Serganova from UC Berkeley, and she will speak on geometric induction for algebraic supergroups.
Okay, thank you. I would like, this is almost the last talk, and the last talk is given by organizers. So I would like to thank organizers for inviting me and for organizing such a nice conference. And I myself, for example, learned 2 new things which are closely related to the topic of my talk, speaking with other people at this conference. So I'm going to speak about geometric induction for supergroups. So I fix for simplicity, I work over C, but any characteristic zero algebraic closed field is okay. And I will consider the simple Lie superalgebras, finite dimensional, and actually with reductive even part. And invariant symmetric form, although last condition is not so important. But essentially, I'm also considering the algebraic supergroup G, which are associated to such superalgebras. And basically, I am going to talk about 2 examples. GLMN and OSP M2N. And there are several ways to look at the supergroup. And what is nice about these 2 algebraic supergroups, all these ways work, and it is proven that they are always work. So one way to look at it is look at the ring of functions, regular functions on the group, and look at it as a Superhof algebra. The second way to look at it would be to consider a functor from supercommutative rings to groups. And the third way to look at them would be to look at a fine supermanifold. G with multiplication. Somehow, when you work with supergroups, the best way to work with them, actually, to describe them, is to look at the second definition. And in these 2 particular examples, the GLMN, the functor, can be realized as the matrices with coefficient in some superring, commutative superring R, such that A belongs to M. So R is a supercommutative ring, so it has Z2 grading. And you can think about matrices. But not all, of course, not all matrices, but invertible. M by M matrix, D, and yeah. But you can say the matrix is invertible. It's easy to prove it. That means that A and D are invertible. It's just a statement, actually. For OSP, all you can think about it as actually the endomorphisms, even endomorphisms of the vector superspace of dimension M. And the OSP M to N can be considered as an endomorphism we preserve non-degenerate symmetric even form, even bilinear form. So by geometric induction, I mean the following thing. If I take a subgroup P and G, then if I have V some simple P module or some a finite dimensional P module, when I can make a vector bundle on the supervariety G mod P, and the functor gamma I, which is going to be derived function, generally speaking, will be from category of P modules to the category of G modules. And it is the following thing. If I denote by curly V the corresponding vector bundle, then I'm going to have the cohomology of this vector bundle, practically speaking, but I need to do a little bit of dualizing here just to get rid of going to the opposite barrel, etc. So this is the definition. And basically, I'm interested in the case when P is a parabolic subgroup. Oh, yeah, sure, I planned to do it, but I can explain it right now. It would be good. Thanks. So one way to define it would be the following way. You can take, first of all, you can speak about a functor, an algebraic supermanifold. You can define it as a functor, which is a functor from supercommutative algebras to the sets. But there is another definition, because actually not every functor was working, representable functor. And this is the following thing, a supermanifold is X is, first of all, a usual algebraic manifold X0. With the sheaf on it, which is called a structure sheaf OX. And with the natural embedding of X0, the usual algebraic manifold to X. So the conditions on X should be the following, that locally X is isomorphic to the structure sheaf of X0 tensor with some exterior power of certain vector bundle. This vector bundle really can be described as a conormal bundle to x0 in X. Okay? And if you want, for example, to prove that it's pretty easily to construct a functor here.
But you haven't really said what X is.
No, X is nothing but the sheaf on, or so what is X? What's embedding of x0 into X, that basically means that you have a projection from this sheaf OX to the sheaf x0. Okay, that's basically what it means. And the condition must be that locally we have such an isomorphism.
But you regard a simple manifold as an algebra of functions tensored with a Grassmann algebra.
Locally.
But so what does it mean globally? I mean, you have to glue things together? at
You
some
do,
point?
yes, you gluing you can define them using the gluing things together as well. Yes.
Does it ever come into, oh.
Yes, it does come in all this business, really.
Even in the super part, or is it just that localized, as it were, on the user?
I know, you know, when you start gluing things together, your odd variables are going to appear. And this is very important. It's really important. So, before I can continue with discussing this functor here, I would like just remind everybody, which everybody already knows very well, what happens if G is just a reductive group and P is an algebraic subgroup. When there is this famous Borel-Weil-Bott theorem, so suppose a lambda P be a simple P module with highest weight lambda.
P is what? Parabolic.
P is a parabolic. I'm explaining the case that P is a parabolic. And then gamma I, GP. So when I look at the weight lambda, it is not necessarily dominant. It's only dominant with respect to P. So if my P is Borel, I don't have any conditions on lambda except it's to be integral weight. So I pick up an element of the Weil group which makes lambda dominant with respect to G. So let's consider the action which is shifted action by rho. So the cohomology appears only in one degree, but this is classical Borel-Weil-Bott, nothing more. And this degree is exactly the length of the corresponding element of the Weil group. So the interesting things happen for supergroup, and it's quite contrary to this example. It is interesting, and people also know that it's kind of interesting in characteristic P, because what you get in such a way is called Weil module, which is kind of very important in characteristic P representation theory.
So you need some extra condition then, stabilize on this.
No, yeah, if, yeah, I forgot to tell, yes, of course, but if lambda is not regular, if lambda is not regular, when we just don't have cohomology at all.
And I suppose W lambda is dominant.
W dot lambda is dominant, right? the mean dominant. So my W is chosen in such way that it makes it dominant. So I would like to mention now a little bit of the history and say that certain stuff about this, people started, at least what I don't know about it is, was started by Manin in 80s with his students, so I write down several names. The geometry of G mod P was studied in the 80s by Manin, Penkov, Voronov, Gaevetsky, Skornikov. So I was an undergraduate student at that moment, and there was also a lot of what was discussed at this moment at Manin's seminar. So for example, some Schubert cells were described, and some other interesting things were discovered about G mod P. For example, it was discovered that G mod P not always is projective, so it not always can be written by the set of equations in superprojective space.
When you say that, you mean, what do you mean exactly?
Oh, for example, this is a very known theorem that if you pick up a highest vector and you consider the orbit in a projectivization, this is going to be G mod P in usual case. And this G mod P, any G mod P can have such a realization. So in super case, it doesn't always work.
Oh.
So in particular, for myself, an important, now before I go to this, I would like to say that people especially are hating supergroups. There is a way to describe this functor without going to the supergroups on the level of superalgebras. And this is the use of Zuckerman functor. We derive Zuckerman functor. And it was done by Sanchez in his PhD thesis, and this is the student of Michel Deflot. So you can actually define everything using this derived Zuckerman functor. When you take vectors, G0 finite vectors, basically. So you induce from the parabolically induce, co-induce, take the G0 finite vectors and then take dual, and you get exactly the same thing.
And I presume you don't need the original model to be finite dimensional.
Generally speaking, no. But you see the results.
Is anything known about the non-finite dimension?
Anything reasonable about non? In this setting, when you take G0 finite vectors, no, really, I don't think so.
So vanishing in particular. For
Vanish.
example, you have a very powerful vanishing theorem here, but do you have a corresponding vanishing theorem when you don't take simple models to begin with?
No, I don't think so. I don't think anybody looked at it. And this vanishing theorem, by the way, doesn't work usually. I will. Even in finite dimensional case, the case is so interesting that people, I believe, didn't go further than that. Fine. But the particular result which I want to mention now is this, the theorem which belongs to Penkov. Suppose that lambda plus rho and then product with any odd roots. So in superalgebra case, you have even and odd roots, which I hope I don't have to explain. For any odd root, then Barré-Veilbois theorem exactly works.
You mean every rather than any?
For any odd root,
For every. Yeah, well,
for any p, yes, for any p.
for every.
I think he actually proved it for b, but it's true for p as well. I mean, you can easily do it. So the weight which satisfies this condition is called the typical weight. But in general, it is known that this is not true. What?
No, I understood that any and every is the same in Russian. I heard. That's what.
Is it not? Is it not? I
Any
never.
and every is the same in Russian.
More or less what you mean.
Okay, so now I'm going to tell you something else. It's related to this definition of. This is related to the supergeometry a little bit. So it is related to this definition of the supermanifolds, which I just gave. You see, you have, if you define a supermanifold, you have a canonical embedding of the usual manifold inside it. And so you have an ideal, you have the map. And then the kernel is the ideal of x0. It then consists of nilpotent elements. And therefore, this ideal actually, the powers of Ix define a filtration. And therefore, you can consider as well the graded, associated graded. And let's again define another supermanifold. And if X happens to be isomorphic to X is called splitting or splittable. And for example, if you study the groups, algebraic groups, which I mentioned before, they are all splittable supermanifolds. But this is not so for Gmod P in general. They're not splittable. They're quite interesting. So now suppose I'm going to use the problem of calculating cohomology of certain vector bundle. Then, of course, cohomology of X in some vector V, bundle V do not coincide with the cohomology of the graded vector bundle. But by general nonsense, the Euler characteristic in both cases is going to be the same. And so, if I would like to study the value of this induction functor, I do not know, it's rather difficult to figure out, for example, the Chern character of the cohomology, but it would be rather simple using the usual Barré-Veilbois theorem to write down the character of the Euler characteristic. Because you see, grid G mod P have a vector bundle on it, can be easily described as certain G0 sheaf on the underlying usual variety G0 mod P0. And combining the while character formula with Borel-Veilbord theorem, with this remark, one can get a following formula for the character. Now, in my talk, delta means roots. Delta 1 means odd roots, and plus means positive roots. So this formula looks very much like the wave character formula, while character formula, sorry. Anti-symmetrization over the while group, and the while group is the while group of underlying G0. So this is a nice polynomial, which it is written in exponential form, and I just was quite happy to know recently at this at this conference from Sasha Sergeev and Sasha Veselov, that for certain cases of GOSP and for certain parabolics, they appear as solutions to some deformations of Kala-Zero-Moser equation. So they're kind of interesting by themselves, these polynomials. It would make us interesting to study them. So now I'm going to speak about application of this geometric induction function to certain questions of representation theory of Lie superalgebras. Before I do it, I would like to say that combining the proposition of Pentov, which I just erased, so Borel-Veilbord for super case, which is actually written here, and this formula, one very simply gets the character of any typical finite dimensional representation. So from this, you get formula for character of a lambda, if lambda is typical. Of course, this formula was obtained by Victor Katz in 1977, I believe, by other methods, but it's just illustration how, or maybe 78, I don't know. So how this works, but this is a very simple illustration. So basically, I'm going to discuss two questions. The character of finite dimensional representation, and what one can say about So since the category of finite dimensional representations over a supergroup is not semi-simple, one can ask a question about extensions. So something about extensions. And at least for the first problem, there's a big history, and I just want to mention several things. So people were studied it after Katz published a paper about characters of typical representation. He asked this question, and people studied it for many. There are many works, different works about it. Again, I would like to mention the work of Sasha Sergeev, which he proved Schur-Wald duality for GLMN, which was very beautiful. And it gives partial answer to the question. So in '96, I published the solution for GLMN using this geometry. And later, with Penkov, we did it for the superalgebraic UN, which I not discuss in this talk. And I also wrote certain recursion without proofs for OSP. In '98, but then I dropped the subject because I thought, I know how to do it, why should I bother to doing it in detail? But in 2002, John Brandon published a paper which quite remarkably relates GLMN representation with GL infinity, certain bases and certain representations of GL infinity, and reproved the result completely different method. And recently there are several works of Katarina Stropel and Brandon, which also makes actually they were able to construct certain nice description using categorification, endomorphism of projectives, projective generator for GLMN, using the Havanov approach and diagrams, which is very beautiful. And this was one reason when I started to think about it again. And the second reason was that I got a lot of emails from physicists who were asking me how the algorithm worked for OSP. So they were really interested. And so I decided to finish with work and to understand better the relation between my result and Brandon's result. So what I'm going to talk today is based on two papers, one with two different collaborators. One is Ian Masson, another was Caroline Gruzon. And they basically, this one basically studies the relation between two algorithms, mine and Brandon, and this one basically gives a precise algorithm for calculating character for OSP. And when we wrote this paper with Gruzon, I realized several things which were completely new for OSP case. For example, that there is another interesting thing in super case, that you have more than one complete flag variety. So you can more than one barrel in non-isomorphic. There are several classes of non-isomorphic barrels, and choosing this barrel is kind of very important, and it plays an important role. And actually, the barrel that we choose for OSP is quite interesting and new. So let me start. So also several results are very general and work for any simple superalgebra with the form and reductive part. So first of all, I would like to say that as one can read in Katz's paper, the Lie superalgebras, classical V superalgebras are of two types, type 1 and type 2. And they are a little bit analogous of the symmetric spaces of two types. Because in the first case, the G0 is semi-simple. Oh no, sorry, here G0 is semi-simple. And here G0 is reductive with one-dimensional continuous center. And so therefore, actually, sometimes for many questions, life is much easier in the first case than in the second. And GLMN is of the first type, or OSP is of the second.
Not over.
Not only, but I'm talking only about examples. I know all. Yeah, there are some interesting superalgebras which I completely don't have no idea how to work out.
No, I mean OSP 2 to M.
Oh, all right. There is a special case. But somehow I'm going to treat it like this case. Oh, by the way, that was solved by Van der Jogt and somebody else before. So there is a small case which can be treated in both ways. So the first thing is, let F now be the category of all finite dimensional representations of G. So then the highest weight theory works, and you have irreducible objects or simple objects, which are enumerated by certain integral weights with dominance condition. And we have enough projective covers of these things, projective. But in type 1, you have also an analog of Verma module, which is called Katz module, type 1. There is also Katz module. And so in type 1, the category is actually abstractly, there is an abstract notion of highest weight category. So the category F in type 1 is highest weight category. So I will tell quickly what is the Katz module, because it's a very simple thing. So you see that naturally the resolution of superalgebra GLMN has the grading so one can do the following thing. One can, this itself is a parabolic subalgebra, and so one can induce. And because the complementary subalgebra is probably what, you get a finite dimensional module. And so laws will play the role of Verma module in this category. And geometrically, actually that means that if I pick up the correct B, namely the B would be the subgroup of upper triangular matrices, then G mod B is splittable. And if lambda is dominant, we do have cohomology only in 1 degree, namely in 0 degree. And this cohomology will be this Katz module. So for type 2, one should do something else. And one should find the analog. And the analog is not going to be a module anymore, but it's going to be some element in the Grothendieck ring. Namely, let me now go to the type 2.
Algebraically, is this just some homology with respect to a
Constant theorem.
subalgebra?
Constant theorem.
Well, I don't know, maybe. I don't know.
No,
So what's your-
general unit resolution, I don't think it works. But you can do
Did you
Zuckerman.
said before that you could make everything.
Zuckerman
algebra.
factor, yes.
What?
Yes. So that means that if you take a Fermat module and you take the maximal quotient, it's going to be maximal finite dimension quotient is going to be this.
But is there? But you're writing down the derived. I mean, you're writing down gamma r. But can you write it down as the homology with respect to some Lie
For
subalgebra?
n minus.
Yeah.
Uh,
I thought that's what you said, that everything could be turned into Lie algebras.
I probably can, but I'm not ready to do it right now. I probably can. Because it's, you cannot take the homology in irreducible representation. You have to take them somewhere else. I can't figure out right away where. It might be that I have to take it in this module itself, so maybe not very interesting. I'm not sure. So now what I'm going to do for any weight lambda, dominant integral weight, now basically I'm going to talk about the type 2. So I'm going to define the parabolic Q lambda. First of all, I define fix the barrier subalgebra.
But it also works for exception.
Yeah. It works, but I didn't write it up yet, but I think it works. So we fix the barrier subalgebra, and for the specialist, the barrier subalgebra I fix for this is going to have maximal number of isotropic odd roots. So it's quite opposite to the barrier subalgebra which I use in GLMN case of odd simple roots. So when define Q lambda being a maximal parabolic, such that lambda defines one-dimensional irreducible representation of lambda.
Containing B, I suppose.
Yes, containing B.
But you're confusing us by jumping between groups and algebra.
Defines one-dimensional representation of Q lambda. And I denote by E lambda an element in the Grothendieck group of G, which is exactly this earlier characteristic I was talking before. It is a virtual character, it is not usually, it might have negative terms as well as positive terms. But what one can prove, that if I would like decompose E lambda in terms of irreducible representations in the Grothendieck group, I have such sort of decomposition. And with the natural order on the roots, the coefficients going to be 1 for mu equals lambda, and the matrix of decomposition is going to be triangular. So therefore, if I do know these coefficients, I basically can solve the question of character, because the character of this is known. So now how I do this? I am unable to calculate this cohomology, but I can do something else. So I'm saying that there is a flag of the parabolic, all containing Q lambda, satisfying the following condition, that gamma I pj minus 1, j plus 1, and lambda of pj plus 1 is a semi-simple SG module for I greater than 0, and for I equal to 0, it is almost semi-simple. Because there is always a natural projection, so the gamma 0 is always the highest weight module with highest weight lambda, which is not difficult to show. So I have the exact sequence like this, and everything which stands in this kernel is semi-simple module again. So now to calculate earlier characteristic, to calculate this element in the Grothendieck ring, I consider the step-by-step process, sort of induction, which I'm going to explain now.
And about this gamma I, you said is semi-simple as what?
As PJ model, because you see, the functor is from PJ models to PJ, from PJ plus 1 module to PJ module.
So all are PJ.
All are PJ modules. So moreover, I can calculate these functors, okay? So it's possible. I don't know actually about the time, so I might be not able to tell the answer, but it is possible to calculate all these in combinatorial terms. And then it is convenient to introduce the generating polynomials for these elements here. So if I have two parabolics P and Q inside G, I can define KPQ of small q be the sum of multiplicities of L mu q inside gamma I G mod, sorry, Q mod P, sorry, excuse me. Q is smaller, right? So gamma I P mod Q L lambda Q. And then I take multiplicities of L mu P. In the Grothendieck group, and I take u to the I. So it's going to be the polynomial whose coefficients are integers, but they might be negative integers as well. So for Euler characteristic, my question is how to find out k lambda mu g q lambda for all mu of -1, because the Euler characteristic is getting when you put q equals -1. So I'm saying that it is enough to calculate it for each step, pi over pi plus 1, and then to get it all together. And that follows from the following picture. If you consider the natural bundle, like he is here, then the fiber is going to be again a flux, a certain super flux variety. Who's bigger here? I'm so sorry, wait. Q is smaller, so it's going to be on top. And what I can do the Leray spectral sequence for this. Which I don't know if it is degenerates or not, but at least I can tell something about Euler characteristic. So the Euler characteristic of the bundle here is going to be equal to the Euler characteristic of these things here. And that could be rewritten in the form for polynomials in the following form, count lambda mu g p equals the sum evaluated at -1 equals the sum. Oh, here I should be careful. So applying this several times to this tower of parabolic, you can get the answer for k lambda mu. Now I think I have about.
What's that up at the top? Is it the gamma sub I or what?
Gamma sub I. Gamma sub I.
So you're somehow, are you trying to say that the if you look at G over Q lambda,
Yeah.
that the contribution to the gamma sub i's of that is exactly coming from the gamma sub i's of the P of the individual steps.
More or less, yes. More precisely, it's here. It's going to be the big term. Yeah.
Sorry?
I'm saying yes.
Yes, that's what you're saying.
But that's what I'm saying. Here I wrote a rule. You have to write it n times, k times. But you get basically that. That's what I'm saying, yes. So it's kind of interesting result because I don't think it's true in finite characteristic, for example. Whenever P you take, you never get something simple like these simple, semi-simple modules or over semi-simple modules. It's also, because I don't have time, unfortunately, to speak about combinatorics, I better say something about extensions.
The fact that you can do this is related to this choice of Borel?
No, this is always so. I think that this part of the theorem, real calculation depends.
Oh, well, that's what
The answer,
Yeah, yeah.
the answer, which unfortunately I don't think, I have about 5 minutes, right?
Okay.
So, but what I can do the answer, and it depends on the choice of Borel. Well, the whole procedure is very general.
Okay.
But does this put a bound on the degree of the, well, the bound
Degree of this
I?
polynomial,
No, the
certainly,
bound on the I for which you can get non-zero terms.
yes. The bound of the I is the dimension of the corresponding flag variety for the
The bound
corresponding
on the
legal.
I should be somehow the dimension of P, the minimum dimension, no,
No,
the
no.
maximum dimension of
No,
Pj.
because here, you see, I add them up. I and j here, I add them up. No. But you see, there is a lot of cancellations, actually. Because, for example, when I do it step by step of GLMN case, I have many different cohomologies. But when I end up, and instead of q lambda, I use b, I just have only zero cohomology, because a lot of things cancels here, because I have some negative coefficients here, and they cancel. And what I did, another thing, I realized how they cancel really and combinatorially, but I don't have time to explain it now. I just want to say something which I have time to explain. And this is that this stuff is it has a little bit relations with extensions. So in all these categories I discussed, suppose I would like to know what is extension between two simple modules. Since actually the category we are talking about are all have a duality functor, it's clear that extension group are the same if I change mu and nu. So the one proposition is the following, that suppose mu is less than, or first of all, the things should be comparable if such extension exists. That's also a basic thing about order of weights. If such extension exists, either mu is less or equal than nu, then vice versa. And there is no self-extension. Suppose mu is less than nu, then if extension is not trivial, then in fact L nu appears in this cohomology group for some j in the zero. Multiplicity of L nu of Pj is non-zero in gamma 0 Pj plus 1 L mu of Pj plus 1. For some j might be different. And in this case, if it is such, it is always 1, because this multiplicity is always 1, and it follows just from calculation. So So once again, actually, I would like to say that to formulate a combinatorial answer, we use the way diagrams and technique introduced by Stroppel and Brandon. And we can express the answer in terms of summing over the path of certain graphs, but it requires about 10 minutes to talk about it, and I don't think I have time for this. And I would like to mention just one open question before I finish, because this is if I go back to this remark about degree type 1 and type 2 and highest weight representation, there is the fact which is called BGG reciprocity. Which is that we have basically the multiplicity of the Katz module and P lambda equals the multiplicity of irreducible module in the Katz module. So this is proven by Zhu for GLMN. And for OSP, I suspect that the truth is that this E lambda element of the Grothendieck ring must satisfy certain BGG reciprocity. So the question is, what kind of BGG reciprocity, if there is a kind of BGG reciprocity in this case? I think I stop here. Thank you.
And why do you have some simplicity up there?
Why? Actually, the only way I do it, I just calculate and I see that it is so. I use certain contour gradients. I use the translation factor for the proof. And I studied a certain exact sequence. And there is some condition which, this is a calculation. I don't know any good explanation for this fact, geometric explanation so far. Just a fact.
And what is new for exceptional?
So for exceptional, first of all, they defect 1, so the maximal degree of atypicality is 1. So you can construct all this stuff, but the only thing which was done by my student Nina Nemirovskaya for D21 alpha and her PhD thesis, and I think she also did G3, but she didn't write it up. So, but I think program works. I just need another greater student to do it. Yeah.
Are there other questions? Thank you, speaker.